So 7.3 part 2, and we're going to talk about partial fractions. Now the idea that we're talking about today, partial fractions, is it's related to rational functions that we talked about in chapter 2, and it's also related to systems of equations. But we're learning it because it's something that you will apply in calculus. I know that in Calc BC in the last week or so, Ms. Hine, their class they were using partial fractions as a tool to solve a certain kind of problem. In Calc 2.3, if you're a sophomore and you take Calc 2.3 here, we use partial fraction for several different kinds of things. So they're a tool to solve a different kind of problem, and are related to things that we've been talking about, so that's why we're talking about them now. So the idea with partial fractions is we have it. Back in chapter 2 we talked about functions, rational functions that look like 3x plus 1 over x squared plus 2x minus 3, for example. What we want to do today is we want to undo finding the common denominator and adding. So we want to take this fraction back into pieces. So we can, if we were to do that, and we'll talk about how we do it today, we would find that f of x equals 1 over x minus 1 plus 2 over x plus 3. So if we took it apart, this would break apart into these two fractions. We call each piece of these a partial fraction. So each one of these is a partial fraction of this fraction, and we call this whole thing together the partial fraction decomposition. So the process of taking this thing apart into this is called the partial fraction, is called decomposing with partial fractions, and this would be the partial fraction decomposition of this, and each of these pieces would be a partial fraction. And what we're going to do is talk about how we do this. So we are working with, we have some rational function, and we're going to call it n of x over d of x, like we did in chapter 2, numerator over denominator. And we have several steps. It's a lot like solving systems. We end up solving systems as part of this, but it's a very mechanical process. And once we see how it works, it's not really a difficult process, just kind of mechanical. So we have our numerator over denominator. The first thing that we're going to do is we have to use long division if this fraction is improper. Now let's remind ourselves what we mean by improper. If this fraction is improper, what do we know? The degree of the numerator is greater than the degree of the denominator. So I'm just going to say degree of n of x is larger. So if the degree of the numerator is larger than the degree of the denominator, we have to do long division. And then we have to use partial fractions on the part, not the part that's above our division sign, but on the remainder divided by the divisor. So we have to use partial fractions on that piece. So that's a step that, if it's improper, we have to do that first. Our second step, then we're going to factor we want to factor the denominator. Let me pause this. And we know that when we factor the denominator, we're going to get either linear factors or quadratic factors. We can always factor a polynomial into linear factors and quadratic factors. That's one thing we figured out in chapter 2, is that's always possible. So we're only going to have two possibilities in the denominator: linear factors and quadratic factors. So for each linear factor, and our linear factors are always going to look like px plus q, and we could have some power of that, and I'll say to the m power. So we could have a bunch of linear factors when we factor this, and we could have some powers. For each linear factor, we need these fractions. I'll say partial fractions. So we're going to write a1 over px plus q plus a2 over px plus q squared plus dot 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 all the way up until we get to m, plus a to the a sub m over px plus q to the m power. So we have to have one partial fraction for each power of each linear factor. So if this is the third power, we're going to have this second power, third power. So we're going to have 3 partial fractions for a linear factor that's to the third power. So that's one possibility. And then we could have quadratic factors also. And our quadratic factors are going to look like ax squared plus bx plus c. We need these partial fractions. So the only difference between our linear factors and our quadratic factors is, instead of a constant a1, a2, a3, dot, 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 am, are just constants. A's are just constants, just numbers. So we need these partial fractions. We're going to have b1 x plus c1 over our quadratic factor, ax squared plus bx plus c plus b2x plus c2 over ax squared plus c squared plus dot 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 all the way up to, and I'm going to say we could have powers here, bn x plus cn over ax squared plus bx plus c to the n power. So we need one partial fraction for each power of our quadratic factor. And the a's, the b's, and the c's are just constants, are numbers that we have to figure out. And we'll talk about how we figure those out in just a second. Now this sounds kind of complicated. It's really not. It just explaining it makes it seem a little complicated. We just include one partial fraction for each factor and each exponent of that factor. So what I want to do next is just list out how we would break down a rational expression into partial fractions. And then we'll talk about how we find the a's, the b's, and the c's. All right, so the first step, if it's improper, we do long division. We do the partial fractions on the remainder over the divisor. Then we have to factor our denominator. Our factors in our denominator are going to be linear or quadratic, and we need to include one partial fraction for each factor and each possible power of each factor. So let's look at how this breaks down. Once we see a few examples, it should be pretty clear. All right, so let's say we have, and I'm just going to use the same numbers every time, just different factors in the denominator to show how this is going to break down. So we're going to break this into partial fractions. I have two linear factors, no exponents, so I would break this down into a over x plus 1 plus b over x plus 2. And then I would use the process that we're going to talk about to find a and b. Just one linear factor, so I need one partial fraction for each factor. If I had 3x plus 5 over x plus 1 squared. Each one of these is different. I just want to show you how we break them down. So here we have linear factors, but this one's to the second power. So I have a over x plus 1 plus b over x plus 1 squared plus c over x plus 2. So I need one partial fraction for each power of this, each possible power. If I had 3x plus 5, and on the denominator my factors were like this, then I would need two partial fractions for the x squared, a over x plus b over x squared, one partial fraction for the x plus 1 factor, and three partial fractions for this. So that one's pretty long. We won't be doing anything that's that long today. But I just want to show you how we break it apart. One partial fraction for each possible power of the factors in the denominator. And let's look at a quadratic factor. 3x plus 5 over x times x squared plus x plus 1. We can't factor x squared plus x plus 1 any further. We can't factor that anymore, so that's a quadratic factor. So we would need one partial fraction for the x, a over x, and one partial fraction for the quadratic factor, and we'd have to write that as bx plus c because we have this quadratic factor. And then finally, let's look at a power of a quadratic factor. We have two of these, so I could say that's ax plus b over x squared plus x plus 1 plus cx plus d over x squared plus x plus 1 squared. So we have these, the numerator has to be in this form for our quadratic factors, and then I have one factor for each power that's in the denominator. So that's how we break those down. That's what the rules that I just said, that's what they tell us to do. And we can always factor until we end up with linear factors and quadratic factors. We can always factor a polynomial that way. All right, so let's talk about how we find these A's, B's, C's, and D's, and what that has to do with systems of linear equations. So questions on what I did here so far? Okay. Once you factor, it's a pretty mechanical process. So let's do the partial fraction decomposition of 3x plus 1 over x squared plus 2x minus 3. All right, can I factor that denominator? Yes? How does this denominator factor? Plus 3 minus 1? Oh, yes. All right, so we factored our denominator. We don't have an improper fraction, so we factored our denominator. So we need to include one partial fraction for each of these factors. So that's going to be a over x plus 3 plus b over x minus 1. Now what we do is always, when we're using partial fraction decomposition, we're going to multiply both sides by the least common denominator. So I'm just going to write it, this time I'm going to write it out. We don't always have to write it out. So I'm going to multiply both sides by x plus 3 times x minus 1. So I'm multiplying everything by x plus 3 times x minus 1. And then on this side, both of these cancel out. On this one, this factor cancels out, and on this one, that factor cancels out. So once I multiply by the least common denominator, I can write 3x plus 1 equals a times x minus 1 plus b times x plus 3. Now I'm going to distribute. 3x plus 1 equals ax minus a plus bx plus 3b. Now I'm going to get all the parts with the x's together and all the parts that are just numbers together. So 3x plus 1 equals ax plus bx minus a plus 3b. Now once you do these a few times, some of this process you can kind of combine some steps together. I'm going to factor out the x here. So this is a plus b times x minus a plus 3b. These two sides of the equation have to be equal all the time, no matter what. So that tells me that whatever's in front of the x here has to be what's in front of the x there. And whatever is a number here has to equal that number there. So I can write a plus b equals 3 and minus a plus 3b equals 1. And now I have a system of equations. Two equations, two variables. Add these two equations together, since if I add them together, these a's go away. Add them together, I get 4b equals 4. Just want to put it in the back. 4b equals 4, so b equals 1. A plus b equals 3, so a has to equal 2. And then I rewrite my partial fraction, so this equals 2 over x plus 3 plus 1 over x minus 1. So I've broken down this fraction into its partial fractions. Using this process and setting the numbers equal to the numbers and the coefficients on the x equal to the coefficient on the x on this side. Questions there? All right, let's look at another example. Go back here. Do I want to do this one? Let's say we have 2x squared minus 3x minus 1 over x cubed minus x. All right, it's not improper, so we don't have to do long division here. But can I factor this denominator? So I get 2x squared minus 3x minus 1 over x times x squared minus 1. Can I factor x squared minus 1? Yeah. X plus 1, x minus 1. So I have 3 linear factors. So this is going to be a over x plus b over x plus 1 plus c over x minus 1. And I'm going to multiply through by my least common denominator. That's this whole thing. So when I do that, I get 2x squared minus 3x minus 1 equals, I'm going to shortcut this process. We don't need to write this out, hopefully. So what does a get multiplied here by? If I multiply through by this whole thing. X plus 1 times x minus 1. Plus b, what does b get multiplied by? X times x minus 1. And c gets multiplied by x times x plus 1. So now I'm going to multiply this out. This is x plus 1 to x minus 1 is x squared minus 1. So I get a times x squared minus a. Here I get bx squared minus bx. And here I get cx squared plus cx. And this equals 2x squared minus 3x minus 1. Gather all my like terms. So 2x squared minus 3x minus 1 equals, I have a plus b plus c times x squared. For my x's, I have a minus bx and a plus cx. And for just my numbers with nothing else, I have minus a. I'll put it in there. Thank you. And now I can equate this part with this part with this, and this part with this. So I get a plus b plus c equals 2, minus b plus c equals negative 3, and negative a equals negative 1. So this tells me this is my system of equations. So this tells me that a equals 1. And from this one I can figure out that c equals negative 3 plus b. And I'm going to substitute these into this first one. So I get 1 plus b minus 3 plus b equals 2. So negative 2 plus 2b equals 2. 2b equals 4. And finally, b equals 2. And if b equals 2, then c equals negative 1. Plug that in here to get c equals negative 1. So that tells me that this fraction equals 1 over x. B was 2 plus 2 over x plus 1 minus 1 over, the c is negative 1, c over x minus 1. And this is the partial fraction decomposition of that rational expression. Questions on the process? So in calculus, we'll use partial fractions. This process is a piece of a bigger problem. So you have a problem, you have to use partial fractions to come up with this 1 over x plus 2 over x plus 1 minus 1 over x minus 1. That's not the solution, that's a piece of the problem. So this is one part of solving several particular kinds of problems in calculus. We use it for what we call integration. We use it for finding sums of series, and it also shows up in solving a kind of equation called the differential equation. So it comes up in several different places. All right, I want to look at one example with a quadratic factor. All right, so we want to write the partial fraction decomposition of this rational expression. So what's our first step? It is not improper. How are we going to factor that denominator? What can we do to that denominator? Multiply by, or factor out an x? Can we factor x squared plus 4x plus 6? Does that factor? No. So we have a quadratic factor. So our partial fraction, we're going to write our partial fractions. We need one partial fraction for the x, a over x, and then we need a bx plus c for the x squared plus 4x plus 6. Multiply by the least common denominator here, and we get x plus 6 equals, what does a get multiplied by? When I multiply by my least common denominator? X squared plus 4x plus 6. And then the bx plus c, just want to put it in faster, that'd be great. Ends up being multiplied, these cancel, multiplied by x. I'm going to multiply this all out, and this one turns out nice and easy. So we get ax squared plus 4ax plus 6a plus bx squared plus cx. Combine all my like terms. I have an ax squared and a bx squared, so I get a plus b times x squared. I have a 4ax and a cx. And then I have a 6a here. this has to equal the x squared on this side. This has to equal the x part on this side. And this has to equal the number on that side. So a plus b equals what? 0. There's no x squared over here. So a plus b has to equal 0. 4a plus c has to equal 1. And 6a equals 6. There's our system of equations. That tells me that a equals 1, b equals -1, and 4 plus c equals 1. So c equals -3. So our partial fraction decomposition of this is 1 over x plus -x minus 3 over x squared plus 4x plus 6. And that's our partial fraction decomposition. When I first learned to do this, I loved doing this. It was fun being able to take these apart. You put them together, and then now you know how to take them back apart. Taking things apart is always more fun than putting them together. But then you need to know how to put them back together, otherwise things go wrong. All right, questions on partial fraction decomposition. Now I know, just a heads up, this is something that when you in Miss Hines Calc BC class, when you get to there, this is something that she'll say, you've done partial fractions before. I'm not going to teach you how to do it. We're going to use partial fractions. So it's something that she expects that you have seen, and that when you see it again, you'll be like, oh, that's partial fraction. Not, oh, I completely forgot. We need to relearn it. So this is something that you are going to be expected to know moving forward. Just so you know. All right, homework. There you go.